Hello, hello, hello.
Yeah, hi, Kinford here.
Fellow members of GHIE and others who have joined, thank you for coming, and we welcome you to this seminar, which will be quite interactive at the end. My name is KD Lai. I'm doing the management of this seminar in terms of moderating, etc., etc., etc. I used to be the chairman of an electrical division for many, many years in the past. So in the next 5 minutes, we shall start, and then we'll introduce Prof. Joe Darkwa, and then we'll start. So Prof, we're giving you 5 minutes to have a sip of water and prepare your lovely voice so we can start in the next 5 minutes or less. Thanks, Prof. And thank you, everyone. Thanks to everyone for turning up. Sure you won't be disappointed. I think we shall start now. Good afternoon. Sorry. Good afternoon, everyone, and good afternoon to you, Prof. Joe Darkwa.
Good afternoon. Good evening, rather.
Yeah, good afternoon.
Good evening. Good evening to everyone. Thanks for the correction. We are here today, this evening, to listen to and interact with Prof. Joe Darkwa of the University of Nottingham. We're going to be here for about, Prof, about an hour and a half or so. And we are about to start. First of all, I'd like to introduce Prof. Joe Darkwa. Well, before I start, it would interest you to know that Prof is an alumnus of UST. We say UST, but now it's called KNUST. He's an alumnus of UST in our time.
We can see your face.
Currently, Prof Joe Darkwa is a professor of energy storage technologies at the Faculty of Engineering, University of Nottingham, England. He was founding director of the Center for Sustainable Energy Technologies, and director of Key Laboratory for Integrated Thermal Energy Storage Technologies at the University of Nottingham in China. So this man has got experience in China and the UK. I don't want to say good and bad, but he has experience at least Oriental and Occidental. Recently, he successfully led and completed a UK Engineering and Physical Sciences Research Council, acronym EPSRC, multi-million-pound decarbonization projects in the building sector in the UK. He has been a consultant and advisor to London Underground, CIBA Limited, US Gypsum Company. This is just to mention a few because we don't want to keep him there for too long. In 2004, the American Institute of Aeronautics and Astronautics, AIAA, honored him as a distinguished international energy research coordinator. In 2007, they again awarded him for technical excellence in energy conversion engineering systems. Prof is currently an editorial board member of Energy Storage Journal. He's a full member of the EPSRC College and a board member of International Journal of Low Carbon Technologies. He's also a reviewer of many journals on energy and energy conversion and conservation. Well, so members, you can see that we have in our midst a very distinguished, learned, and performing professor. He doesn't look like one. He hasn't got long hair and a disheveled jacket or anything of the sort. He's still a very young man. So members, I present to you Prof. Joe Darkwa. Unfortunately, since it's online, we can still applaud. So Prof. Joe Darkwa, thank you very much for joining us. And members, I think what you'll do is we'll write down our questions because we want the flow to be uninterrupted. When we finish, Prof will be available to answer all our questions. So Prof. Darkwa, welcome very much indeed, and your audience. We can't wait to hear you. Thank you very much. Thank you, Prof.
All right. Okay, Kingsford, thank you very much for organizing this event. And I'm proud and also privileged to be in the midst of your professional colleagues. Like you said, I started my undergraduate career in KNUST many years ago, and I've been doing a bit since I left Ghana. And the project I'm going to talk about is one of the projects that I managed to bring to Ghana, which was funded by the UK government. So I'm going to spend the next half an hour or so to give you some background about the project. And then after that, obviously, it will be more interactive and you should be able to ask questions. Okay. So can I ask Kingsford, can you hear me clearly, from your end?
Yes, please.
Yeah, Prof, I can hear you clearly. I hope everyone can.
Okay, so I'm going to share my screen in a minute.
Okay.
Okay. Okay. Right, can you see the screen clearly, please?
Not yet. I think it's still in traffic.
All right, let's see.
Yeah, traffic has eased.
Okay, so I'm going to put it in the slideshow mode. Okay, is it better?
Sure.
Yes, please.
Oh,
Very better.
okay. Right, so like I said earlier on, I'll spend about half an hour or so to give you the background of the project. And then I'll also try to highlight, what were the reasons, for the project to be awarded. and then some aspect of feasibility study, which was part of the project. Some of the materials that we had to develop as part of the resources that were needed for commissioning the project. And then I would also obviously talk about how the system was designed, and then talk about the commissioning, testing, and then the way forward. Okay, so it's all about a project which was initiated by the UK government. I mean, to look at how to minimize poverty in most of developing countries. In particular, we're talking about low and middle income countries, which Ghana happens to be one of them. And the problem with Ghana is that if you look at the country, over half of the population live in rural areas. And obviously, these are the areas where poverty is at the highest. So if you want to tackle poverty or minimize poverty, then obviously look at what you can do to improve upon the lives of the rural communities. And you may be aware that one of the indicators or one of the means of minimizing poverty is energy. Energy is the backbone of every country, or the economic development of every country. So what are the problems? I'm sure most of you are aware of the situation in Ghana. It's getting better, but I think we still have a long way to go. Even though poverty level is about 24.3% as at 2024, most of the rural folks, they still live in poverty. And that is something that needs to be tackled. Because, the rural communities, without them, we cannot feed ourselves in the urban areas, in the cities and other areas. So they form a very important part of the whole population. Look at that. Make just a simple comparison. Poverty level in rural areas is about 4 times as high as urban poverty. And I don't think it's getting better. If anything, it's getting worse. Because I think there is massive migration of the rural communities, into the urban centers. So most rural communities obviously are dying. No opportunities, and that is something that is very, very sad indeed. And if you look at the energy situation, I think that is also in decline. Even places like Accra, Kumasi, and other places, the cost of energy is relatively is high, let alone in the rural areas. It's about 5.7 times poverty level. I don't know the definition of energy poverty in Ghana, but in the UK, it's defined as if you spend more than 10% of your income on energy, then you are classified as, obviously energy poor. So that is the level. And if you are spending about 22%, of your income on modern energy, then that is something that cannot be considered to be sustainable. About 80% of households in Ghana use wood, as means of fuel for cooking. And the impact on that, on Ghana's forestry, is quite severe. Apart from that, impact of wood as fuel on the health of women and girls is also very, very high. it affects the fertility of women, and that is something that is still going on. So what are the solutions? I mean, to start thinking about a credible solution for providing energy services for the rural communities, you have to then start look at the resources, because whatever proposal that you put forward should be sustainable. And one of the potential sources of fuel, obviously, is biomass, because Ghana is blessed with a vast amount of different types of biomass, across the country. And one of the resources of this biomass, which is considered to be waste, is cocoa pod husk. If I remember, as far back as when I was a child, and cocoa pods have been left on the farms, to just rot. The beans are removed, and then obviously the husk are left on the farm, and then nothing happens. I remember when we were children, some women would collect them and use them for kind of traditional soap. I don't know whether it's still going on, but the bulk of it are left on the farms, to rot. So if you look at the resources, then obviously we got loads. Yeah, because if you take one pod of cocoa beans, which is a ton of it, you get about 10 times the waste. So 1 ton of dry beans of cocoa is equivalent to 10 tons of the cocoa pod husk. So on average in Ghana, we have about 8 million metric tons per year. And this is waste resources. So what we did was to look at how best we can convert this product into some form of energy. So initially we visited Ghana. It took us about 6 months to visit all the dominant cocoa growing regions in Ghana, and then talk to the rural communities. In other words, to find out what opportunities are available in these communities to use these resources for power generation. That was important because we were not sure about the energy content of this waste material. Obviously, we knew of wood. So wood was used as the reference point for this cocoa pod husk. And then after we've done that, obviously, then we'll be in a position to identify what sort of technology can be used to convert the cocoa pod husk into some form of electricity and also for cooking fuel. So here you can see that there are 2 areas of interest: to be able to produce power, some form of the centralized form of electricity, and then some form of cooking fuel. So we gathered community leaders, went to so many areas, and that was very interesting because some of these areas are so remote that it's difficult to even connect the national grid, to such areas. But these are very happy people doing their farming and then also getting on with their business, but they lack basic energy services. That is a bit of a shame, because since when did we attain independence? And not to be able to provide basic amenities in terms of basic energy services for our rural communities, that is something that I think it should not be allowed to continue anymore. Because with basic energy services, it will go a long way towards improving on health. It will go a long way towards some form of education. And and also creating some form of economic activities, for these rural communities. But without that, then what happens? They are doomed. So part of the feasibility study, first of all, was to map out all the cocoa growing areas. So obviously it was a bit intensive, but that helps us to provide the data, database for the materials that we were looking for. And for the first time, I got to know that there are 4 main types of cocoa pod husk in Ghana. So the cocoa beans that you see around, they don't come from the same, if you like, fruits or the same source. So in Ghana, there are 4 main types, classified as Amazonia, Ameloneda, Hybrid, and then Trinitario. So we identified these cocoa pod husks in different areas of Ghana. And the next step was to find out for each cocoa pod husk the energy content, so that at least we'll be able to know how we can maximize the energy potential for the production of electricity. So what we did was we brought all the samples, to the UK, and then did all the scientific analysis and to do all the classification that we need. But it was very interesting that we also realized that it's only 40% of the cocoa growing areas, have access to some form of electricity. The rural communities were also very, very interested to note that the cocoa pod husk, which they classify as waste, could be converted into some form of cooking fuel and also as a feed for electricity. They were also interested to know that these resources, which are classified as waste, would also go a long way to minimize deforestation in their communities. So what did they say about getting involved? Because the whole idea was to empower them, let them be part of the whole journey that we were planning to undertake. So there was the suggestion of forming some kind of cooperatives. And that was, I think, very, very attractive, proposition to them. Because with the formation of the cooperatives, we came to agreement with them on the basis that there will be 3 main cooperatives, and that they were to obviously organize themselves in all the regions to form those cooperatives. One of them was to be responsible for collecting the raw material from the farms and then dry them. So you collect and then you dry. Another cooperative will be responsible for processing the cocoa pod husk further by breaking them into some form of sizes that we were going to specify. So they will crush them into some specifications that we were giving them. And then the third cooperative, they will be responsible for running the whole system, so that there will be that chain of activities between these 3 cooperatives. And they were very, very interested in being part of it. That is one of our researchers in Kane at the university who, there were about, I think, 20 of them. They did very, very well. So we brought these samples to the UK, and as part of the analysis, we did all the characterization. Because we were interested to know how much energy content after it's been dried, and then after it's also been, characterized, to know how much carbon content and other chemical compositions. So we brought everything to the UK and then did all the analysis. And then we also were able to map out these areas because you can see certain areas dominate. If you take, for instance, Ashanti region, the type of cocoa pod husk in Ashanti region has the highest energy density. So that helps us to maximize or to target certain areas in terms of what sort of resources are needed for the conversion of the cocoa pod husk into electricity. We're also interested in the carbon content. Also, there is a map to show which areas dominate in Ghana. One of the byproducts is the ash content, where we were also interested in identifying how much ash would be obtained from the byproduct. Why we need this ash content as a byproduct, I'll tell you in a minute. But it turns out to be one of the byproducts which could also be converted into some form of economic product. So as an example, you can see here, Ashanti region, different types of cocoa pod husk, and then on comparative basis, the high heating values, and then also the ash content analysis, which, like I said, we were very, very much interested in it. Right, so that helps us to do all this scientific data, and this is a very important data which has never been undertaken in Ghana before, because you got classification of all the types of cocoa pod husk, with all the thermophysical properties, the ash content, the moisture, the carbon, hydrogen, nitrogen, sulfur, oxygen, and then the rest of it. So from scientific point of view, this was a very, very useful exercise, because without this, we couldn't have specified the type of technology that we wanted for the conversion of the raw material into electricity. So as part of it, we organized a workshop in Kumasi, and then invited all the Cocoa Farmers Association, the representatives across the country, and we spent a day briefing them about how the cooperative formation is going to be organized. In fact, we also brought in some microfinance institutions, to brief them about how they can access, finance from these banks to run their businesses. So it was a very useful event which took place at the university. Right. So we've got all this information now. The next stage was to implement the system. So that was to look at what sort of technology that would be appropriate, and then also how the whole system is going to be implemented in Kumasi. I forgot to mention that this project was fully funded by the UK government as part of the poverty reduction initiatives. So every piece of item or system that was purchased was provided by the UK government. In fact, including even the plant room for the demonstration plant. We built everything, provided the finance for it to be implemented. So that gives you a schematic view of the design of the power system, and it's based on gasification power plant. Gasification system happens to be the most appropriate because we were able to establish the importance of using the cocoa pod husk as feed for the gasifier, and also using it also as an alternative cooking fuel. Instead of using charcoal, you can use the cocoa pod husk, which was converted into pellets. And part of the process was to have a simple mechanism for drying cocoa pod husk. I remember when we were children, I'm sure it still goes on. I mean, the cocoa beans are, left on a kind of platform, and then obviously exposed. And when it's raining, you see the elders running to go and cover them. So, in association with our partners, we developed this solar-powered drying system, very simple, which will enable them to dry the cocoa pod husk, and then wouldn't worry about whether it's raining or whether it's not raining. So everything will be, kept in that, structure. And then to make sure that the tunnel doesn't accumulate moisture, we also introduce a solar panel extractor fan. So on top of the tunnel, we got PV panel, which drives very simple, extractor fan just to remove the moisture. So that helps to the drying process and make sure that the integrity of the cocoa pod husk, is kept within the specification that we desire. So this facility was designed locally in Kumasi and then obviously installed at the university. Then we also looked at how to convert the cocoa pod husk after they've been dried into some form of pellets. So here, this is a very simple, pelletizer, which can be run easily in the local communities. By the way, this one is electrically operated, but in a system or in a situation where there's no electricity, they're able to use mechanical means, to drive the whole system. And you end up with this kind of pellets with certain specification. These specifications are very important to ensure that successful gasification can take place. One may ask, where did we obtain these simple equipment? Because if you look at it, it's fairly basic. We decided it should be fairly basic so that at least the locals should be able to maintain them. And also if something should get, broken or any part is missing, it should be easier for them to obtain it locally. Yeah. And also, it will help them also to develop certain skills when it comes to maintenance of the facility. Initially, we were going to get all these components from the UK, but it turns out that it was going to be very expensive because obviously the high labor cost. So we worked with an Indian company, gave them all the specification, and then they built this prototype, for us. Yeah. So it's low cost, but very effective. Well, you can see it works a bit.
Here is the buffer,
Okay.
and here inside is the collar and tie.
It's a bit noisy. Anyway. Okay. Sorry. I need to go back. Sorry. Okay, so that is the gasifier, and then obviously this is the gas engine. So all these components were, like I said, designed based on our specification in India, and then shipped to Ghana. And we then came over with a team of my researchers to Ghana to assemble, and also we were able to get the manufacturer, the Indian company. They brought an engineer to help us to come and commission the whole thing at the university. So it shows you the nature of this gasifier, and then also the engine.
It is 5 kilowatt gasifier system, and this gasifier
And after everything was commissioned, that is one of my senior researchers who came to Ghana for 3 weeks, and then to make sure that all the test data were in line with our design specification. And here you can see.
I just
Show you.
I'm recording.
Okay, so yeah, that was a demonstration of the power plant after it has been commissioned. And through a series of tests that we conducted, we were able to get some output, which gave us the means to work out the power output. For instance, this one, it was operated at 80% load, and it's the maximum power output is about 5 kilowatt anyway. That was how it was designed. But if you run it about 80%, which was the maximum that we could run it, then I think we obtained about 4 kilowatts. So that was not bad at all from the materials that we used. And these are some of the test results. You can see different samples, and then it gives us on average value for carbon monoxide, carbon dioxide, hydrogen, and then also methane. Because it's a synthetic gas, which contains different types of, it's a mixture of gases. And that is what is used to feed the gas engine. You can see the overall efficiency in some of them. Just let me see here. Overall, if you take the energy content of the cocoa, that's average cocoa pod husk, is between 15 and 18 megajoules per kilogram. And this is very, very competitive. If you compare it with dry wood, dry wood is about 17 megajoules per kilogram. So as a product or as a source of fuel, cocoa pod husk is very, very competitive. We were able to convert over 50% of the chemical energy into fuel. 25% of the combustible gas was also converted into electricity. And that is also quite impressive, because even if you look at some gas engines or gas turbines, you're talking about 40, between, if you like, 25 to 40%. So for cocoa pod husk, This is prototype to be about 25%. Then that was considered to be very encouraging. The thing is, for every conversion system, you are bound to get some byproducts, which obviously in the case of cocoa pod husks, you get some amount of tar, char, ashes, and then some liquids in the byproducts, which means if we are able to refine it further, then the gas yield should be much, much higher. Alternatively, you can also use it as a byproduct for other industrial processes, which I will talk about in a minute. We didn't stop at that level after the commissioning and then also the the demonstration, because it's a research and demonstration product, there for research and also for demonstration to potential commercial entities who would like to take it forward into commercialization. But then we did further investigation to find out how we can refine the fuel. In other words, to make sure that the high levels of tar and char can be minimized. So we came with this idea of co-paragasification, of mixing plastics with the cocoa pod husk. And why plastics? Because plastics are considered to be one of the nuisance of products in Ghana. You see plastics everywhere. And I'm talking about plastic, not recyclable plastic or the degradable ones. These are synthetic plastics. And then look at the situation in Ghana, which we were able to analyze. About 3 million metric tons, it's only about 2% are being recycled. They dump them. I mean, that picture was taken at, I think, James Labadi Beach. No, I think between Labadi Beach and somewhere. Not the proper beach, but other places. And the other one was at, I think, Kole Lagoon. Yeah, it's a dump. It's amazing. It's not, a nice sight at all. But there are plastics everywhere. And most of these plastics cannot be recycled. These are the synthetic ones. So once again, what we did was to collect samples of the commonest types of plastic waste in Ghana, and then brought them to the UK once again to analyze. And this is what we found in Ghana: 4 main types of plastics, synthetic plastic, which cannot be recycled all over the country. All over the country. So we did the normal characterization, also to find out the composition of this, the energy content in each plastic, and then look at how we can combine what proportion of plastics will be needed, as an additive, to the cocoa pod husk, and then find out if that would be enough to reduce the amount of the char and also the tar, and then see the impact on the yield. That also took us about further 6 months to do all that. So we started from the theoretical point of view, and the whole idea was, if we were to raise the gasification temperature beyond the normal temperature, then we should be able to remove most of the char and then also tar. And then that would ensure that the byproduct will not be as bad as if we were to use cocoa pod husk alone. So it was a combination of adding a bit of the cocoa pod husk with each particular type of plastic. Don't forget, we've got 4 different types of plastic. So you take a sample of plastic A, and then you combine it with some amount of cocoa pod husk. And then we do all the analysis to see what do you get out of it in terms of those gases, in terms of all the nasty stuff. So all these things were done through simulations. And then also we did analyze also the effects of these combinations. Here you can see from 10%, 20%, 30%, and also 40%. So it's a process of optimizing these percentages if you combine it with the cocoa pod, and then look at the effect on the volatile yields. So in other words, is it going to give us more syngas or less syngas? So what did we get? We were able to establish that if you mix all the 4 plastics and then you find the proportion of that combined plastics, which will give you the best yield, then about 40% of it, so the concentration is from 20 to 40% at a temperature of 1500 K. What do you get? And then it was very interesting because we were able to establish that the yield would increase from 55 to about 65%. And that was very exciting because we realized, okay, this is also another waste material, which cannot be ignored. It can be used, to contribute to the amount of energy that will be required for the gasification process. Yeah. And one of the advantages also is that instead of sorting out these 4 plastics, you don't have to do that because it's very expensive if you collect them from various places, you cannot afford to sort them out one by one in order to choose which one is the best one. So the investigation enabled us to establish the basis for combining all the plastics and also how much yield can be achieved. So that was the conclusion. 40% of the plastics containing all the 4 types was able to achieve 22% enhancement in syngas. So 22% enhancement in syngas from scientific point of view was considered to be very, very encouraging. Yeah. And the benefit is that it can help Ghana to advance waste management in the country. And then the economic benefit is that you don't have to set up very expensive sorting out facilities from different places because you can mix them to achieve the economic benefit that you desire. So what next? This research and demonstration project has been concluded. The prototype is at Kumasi for demonstration. We've done a lot of dissemination activities in the UK, other places like US. A couple of years ago, where I was invited to go and then talk about it, and then other countries. What is left now is for the whole system to be moved forward towards commercialization. And as I'm sure some of you may be aware, universities are set up to develop technologies. We are not in the industrial entities. So we developed, and then in partnership with the commercial sector to ensure that the technology can be moved forward towards commercialization stage, which requires a risk, it requires investment, and also at times it requires support from governments who view these projects as means of supporting their rural communities. It is a decentralized system. So if you have, let's say, about 5 villages um, surrounding maybe a town, one plant can be provided in a town, and then that becomes the central base or the base for running these facilities. And then the cooperatives can then feed this plant with the pellets. The pellets, like I said, can be used for cooking, and also the same gas can be bottled in small cylinders, for the rural communities to use for cooking. So that is the building which was built during the opening ceremony. In fact, the opening ceremony was delayed because of COVID, but eventually it was done. You can see the plaque, which has been fitted onto the building, funded by University of Nottingham as our contribution towards minimizing poverty in developing countries. So on that note, I'll say thank you very much for listening, and the floor is now open for any questions. Thank you very much once again.
Well, thank you very much indeed, Prof, for your presentation. Thank you for the way you kept us all riveted to what was going on. We thank you very much. It's unfortunate we are not in person, but we are clapping in our various locations. We are applauding. So members and attendees, please, are there any questions for Prof? We intend to be done by about 6:45. So please make your, well, there are already questions. Okay. So Prof, do you want to take a sip of water, or we can go straight in?
No, that's all right. Yeah.
Okay, so we'll start with I'm sorry, Yakubu Sufian. I don't want to say Mr. or Mrs. or Miss because I don't know. So please, Mr. Engineer, okay. Citizen Yakubu, please, let's have your question. Thank you.
Yes, I'm using Mr. Yakubu's laptop. This is Samuel the Dubatia. I happen to be one of the students that work on the project. But when it ends, I have a lot of questions in my mind. And since today I have a chance to meet Prof again, I would like to ask some few questions.
Please go ahead.
So Prof, nice to meet you again. This is Samuel. I was under Dr. Eunice Ajay.
Oh, right. Yeah, I remember Samuel. Yes. How are you?
I'm fine, sir.
Oh, good.
Yes. My problem is the energy balance. I could remember we have the crusher, we have the grinder, we have the palletizer before the gasifier. So my latest work on it was to look at the energy balance. At the end of it, the energy that you use around to get into the final pallet, the final pallet.
Yeah.
Whether what we produce is able to balance out and then make profit. Yeah, so I don't know whether there was another study on it or not.
Yeah. So that is.
Yeah, that's one question.
Okay.
Yes. The second question was, we tried. Another thing we tried at that time was instead of going through the process, after crashing it, we feed it direct into the system. and it was sound to be a little bit economically than going through to produce the pellet.
Okay.
That was another trial that we did.
Good.
And I don't know whether you consider to compare the energy values and the energy value between sending the crush one straightforward and then going through the process to produce the pellet and then use it in the gasifier.
Yeah.
Yes.
Okay.
The third question is we were using starch at the beginning. So I don't know whether you compare the starch and then the rubber, and then you selected the rubber at last minute. So I wanted to get some clarity on that too.
Yeah.
Thank you so much.
Okay. So, yeah, Samuel, that is very interesting questions that you've asked. So first of all, the energy balance. So that is the input and an output analysis of the energy that you provide and then you get out of it. The whole idea is to see how best we can make use of inexpensive, energy input, and it's been assessed that if the rural communities, you see, they can do some of this crushing manually, and then obtain certain sizes. Because the whole idea is, if you break them down, they should be at certain sizes, for you to be able to use it for producing the pellets. And the concept of producing pellets is to ensure that you can achieve two products. No, one product, but for two processes. One is to use it for the gasifier, and one is to use it for cooking. Because you see, if you use pellets, the energy density is much higher. It's much, because everything has been condensed. So the energy density is much higher than just if you crush it into pieces and then use it straight into for cooking or for the gasifier. But having said that, you can also, if you are not going to use it for cooking, then you can crush the cocoa husk to certain sizes and then use it straight away for the gasifier. That can be done. Or you can use it after crushing, convert them into briquettes, and then also use it for gasification. But because the objective was to see if we can achieve two outcomes. One is for cooking, and then one is for gasification. And therefore, using a pellet became the best way forward because the pellets give us much higher energy density. And once you start using for cooking, it cooks slowly, it doesn't burn rapidly, much slower than using charcoal, and then that sustain your cooking process for much longer period. So that is for the that's the reason why the process of going that way through the pelleting way was introduced. The energy balance one, that's something which has to be, that. But then what I was saying, that if there can be inexpensive way of breaking it down and then using it for either for cooking or for the gasification, then that's fine. But the advantage of using the pellet is that the energy density and also the rate of consumption is much slower, and that sustains the whole process for much longer period than the raw broken pieces. Now, talking about the binding additive, which you use starch. Yes, the impact of that using starch has not been verified yet, because I know when I was there, was it last year or 2 years ago, a year ago? Yeah, and then I met Eunice. I saw some samples of starch, which is a binding material, you see. But then, what is the impact of using that as opposed or as against other additives? Is something that we haven't been able to establish or go into that yet because of a lack of time. So there are areas, because I mean, that's why it's a research and development project. So there are still areas that can be investigated. But for the plastics, the laboratory test that we have carried out shows that it helps us to minimize the amount of tar and then also char. And then you are able to enhance on the syngas production. And if that becomes the main objective, then the system has to be reconfigured. Yeah, because it would require different components, to achieve that combination. So what we have done is only theoretical and also at laboratory scale. As you know, it has not been validated in the demonstration plant because that plant is not suitable for the combined plastics and then the cocoa pod husk. Yeah. I hope I've answered your 3 questions, Samuel.
Yes, Prof.
Okay, thank you.
And thank you very much.
Okay.
Thank you, Prof.
Okay.
And
Thanks.
if I may add, the plastic, I mean, the starch has to be produced, manufactured. That will cost some money. The plastics will go and collect and reduce the waste in our country.
Yeah.
Mr. Zakaria, please, it's your turn before the former ED comes in. Yeah.
Okay. Thank you very much. My name is Zakaria.
Okay.
Thank you for the presentation, Prof. I must admit that is beautiful.
Thank you.
I've gained a lot of insights, and I hope to have gotten the opportunity to interact with it personally to see how it feels like to be around such a powerful system. But then I have questions that I needed clarifications on. One is, globally we are moving towards green energy.
Yeah.
As a way of reducing the carbon footprint that thermal energy systems introduce into the atmosphere.
Yeah.
Zakaria, I think you have to reposition yourself because we've lost you.
I want to ask if you have the.
So you are breaking.
Well, I think what he wants to ask is because of renewable energy and pollution. He's asking whether we considered that in this plant, how much this plant is going to contribute to. How much this plant is going to contribute to global warming? That's what he's saying.
Sorry, my network went off.
Okay, so can you summarize briefly before it goes off again, please?
Yes. So I was asking if you have investigated the amount of carbon footprints it leaves on the atmosphere. That is one. Then secondly, if you have tested the system on varying loads, because every load that you hook onto the system has its effects on the system. And then the third one is the possibility of it being integrated onto the national grid. Thank you very much.
Okay. I think I got the last question better than this. Anyway, let me try and then respond. Probably I'll start with the last question about the national grid. The problem with with the national grid is that the system is meant for a decentralized, or is designed as a decentralized system, because in remote areas don't have access to national grid. So
Sorry, Prof, can you hold on for a second? Gentlemen and ladies, please, if you're not asking the question, mute your mic. You're giving us so much disturbance.
yeah,
People's wives and cooking up materials or whatever. So if you're not talking, Mr. Yosin, please mute your microphone. Sorry, Prof. Please, maybe you can proceed. And Michael AO, please mute your microphones. Prof, please continue.
okay, right. Yeah, so yeah, what I was saying was that in terms of connecting it to the grid, that wasn't the idea, because the areas that this system is meant for, they don't have the national grid due to all sorts of difficulties from logistics point of view. The roads are not available for all these things to be provided. So decentralization, where it's meant to be implemented in areas where the resources are available, and then it can be provided for small, communities. And then you mentioned, can you remind me about the second one, please? Because I missed your line was a bit.
Yeah, the first one was about the carbon footprint. Globally, we are moving towards green energy.
Yeah.
So I was asking whether you have investigated the effects it has vis-a-vis the amount of carbon footprints it leaves on the atmosphere when it is in use.
Oh, yes, we've done that, because if you look at the analysis, it gives you the amount of carbon monoxide, amount of you got the nitrogen, hydrogen. They are all part of the mixed gases, which form the synthetic gas, and it's very minimal in the sense that if you compare it with the conventional petrol or diesel, then obviously it's much less harmful than the conventional one. And don't forget the other advantage is that the process of conversion is not through direct combustion, it's through gasification. So that process is less unfriendly than the direct combustion process. So there's a balance. As you know, there is nothing 100% foolproof, but then the level of emission is much less than going along the direct gasification, direct combustion process. With the plastic concept, one area that we are also working on is that the system can also be used to produce biomethanol. Because methanol is one of the green fuels also available. In fact, it's being promoted, in even places like in the UK, because green methanol is very good for shipping. And most of these shipping companies are now looking, instead of either diesel or other type of fossil fuel. Yeah. So that is one other research area that we are undertaking with the company. How you can achieve green methanol or biomethanol from this combination of cocoa pod husk and then plastics. And plastic, like I said, is a complete nuisance. It's everywhere, causing all sort of problems to the country. And if we can use it as means of fuel, then I think it's a good way forward towards making or helping the environment, in Ghana. Okay.
Thanks very much. Thanks, Prof.
Prof, I think I also asked a second one about if you have tested the system with varying loads, because obviously when you connect a purely resistive or probably a combination of resistive or capacitive loads on the system, it behaves differently. I don't know whether you have tested the system on varying loads to know how it behaves and how sustainable it's going to be going forward. Thank you.
Yes, we did that at Kumasi, and the optimum load that we were able to attain was 80% of the full capacity of the system. I haven't got the information here, but we did it for various varying loads and realized that 80% full load was possible up to about 4 kilowatts power output. Yeah.
Okay, thank you, Prof.
Yeah.
And also, I think it's a career. The thing about the varying loads is, oh, sorry. The thing about the varying loads is the fact that we have to bear in mind that this is decentralized generally for small communities and villages, local areas. When we talk about those areas, I mean, the loads are generally resistive. If you talk about, they might have one corn mill here or there, but with proper application of capacitors, etc., we can operate it very effectively on a very small machine. And this is just meant to fill a gap until the time that we stop maybe stealing our money, and then we can extend electricity to all parts of the country. This is like a stopgap measure for a period. Thank you. Engineer.
Okay, thank you very much. I really appreciate the last comment.
Yes, thank you. Engineer Baxton, ED,
yes,
please,
sir.
the floor and the ceiling are yours. Thank you.
Oh, sure. Prof.
Hello.
How you go?
Thank you.
Yeah, Engineer Baxton, the name will ring a bell. A very good friend of Asarabafo. You being our senior. Yes, you being our senior, so it's good. But mine is a very quick one. Okay. You know, so you came in, I knew zero about this project. I've never even heard it anywhere around Ghana. But I'm in Ghana. So of all that you've done, yes, it's sitting at KNUST. Is there any program for it to, seek for investors or something for this thing? And were you going along with ECG and Cocoa Board or whatever in the stakeholders, and you're all tussling in getting this done?
Right. Thank you, Kenneth. Good to speak with you anyway. The thing is, Cocoa Board was one of our partners when we started the project. And then also some NGOs. Yeah. When it comes to taking it forward, unfortunately, all these government bodies haven't shown any enthusiasm as to how it can be, done. And like I said, as an academic or as an institution, we are only available for enabling technologies. You see, we don't do any commercial activities as such. But we do work with organizations to ensure that technology can be sustained. And we are always available. We are always available to support industry. So if you got any idea of introducing a potential commercial entity, I will encourage you to do that because that is something that in the UK the government supports that kind of cooperation between universities and then also the industrial sector. It doesn't matter whether it's a UK company or Ghanaian company. We have schemes, that support such programs. So I would encourage you to explore the possibility.
Okay.
The companies that will be willing to take it forward.
All right. Well said, sir.
Okay, so Professor Darko, can you hear me?
Yes, I can.
Professor Joe,
Yeah.
impressive. I come from the business perspective, so I'm just going to be straightforward. What is going to be the cost of having to set up, a plan like this, an average cost?
Okay, so this particular one was developed as a research and demonstration. Yeah, but if you should look at an average cost for a typical 5 kilowatt prototype, then you're looking about roughly about £30,000 complete for the control system, and it comes in the form of as a package unit. So everything comes in the container, for instance, with all the control panels, everything in it, and it can be moved. It can be moved from location to location. So that is the sort of figure that you'll be looking at to have.
Okay, very well. Thanks.
Similar one.
Yeah, thank you very much.
Mhm.
I'll send you a direct message, so I'll be very glad if you check it out for me when you're done. Thank you.
Okay.
Thank you very much indeed. Please, I can't see any more hands up. If anybody wants to ask a question, please go ahead. We have 5 minutes more to do that. But Prof, whilst people are thinking about their questions, I have a few, if you don't mind.
No, not at all.
Yes, Prof. The gas for cooking.
Yeah.
So we need a special cooker to be able to utilize it.
That is something which needs to be established.
Investigated, okay.
Yeah, because the burner may have to be reconfigured,
Yeah.
because it's not the normal, even though it contains methane, some amount of methane, because it's a mixture of other combustible gases. Yes, the burner may have to be reconfigured to give it the appropriate
Because
combustion.
the injectors for water gas, natural gas don't work as the gases you have where you are.
Exactly.
They don't work for our LPG. So that's
and this is something that if there is a company interested, you see, then it becomes an added value, you see, a product which can be added onto the main component. Yeah.
Prof, you also talked about the pelletizer, that it can be done mechanically.
Yeah.
Do you mean we can use manpower to do the pelletization?
I believe so. And also there is a mechanism that can be adapted to it. Not by hand, you see, but you can have a mechanism of, it's like having a
pulley of something.
Bicycle, something like that, where people will be cycling it.
Right.
Yeah.
Like a pulley system of sorts. Yeah.
So you will be pedaling it, and then obviously to be giving you the energy input.
Well, that's good. That's manpower. That's very good, because where we are thinking of, these people won't have electricity anyway.
No electricity.
And we want to reduce, and thus we have a lot of labor to spare.
Yeah. That is. There are sort of low cost approach that can be. And one thing about the rural communities, they are very good in adaptation and also looking at different methods of doing things. And they cannot be underestimated. Their ability to do things is amazing.
All right. Thank you very much, Prof.
Yeah, thank you.
Are there any more questions? If not, sorry, Prof, I believe people who are interested in getting a record, well, I think the recording has been organized by GHIE. But
Okay.
if we can get, not a recording, if we can get a little, sorry, soft copy of your presentation, because it's something we'd like to move forward. So if, well, maybe we can discuss it afterwards and you tell us where we can find it as an organization.
Okay. Okay.
Thank you very much indeed,
That's
Prof.
fine.
And then now it's time for our vote of thanks. I saw a Eunice online. Eunice, are you still online? Eunice has disappeared. Okay, Prof, I'll do the vote of thanks. What about Yvonne? Yvonne, are you online? No. We wanted some gender balance.
Yes, please, I am here.
Please do us a little vote of thanks. Not too long.
Oh. Okay.
Thank you very much.
Thank
Yvonne.
you. Thank you for the opportunity. Yes. So on behalf of the GHI, would like to thank you, Prof, for and the team and everybody that put in resources to do this research, because it's very useful. A good way of utilizing some of the things we call, let me use the word waste in quotes, and then putting it back to good use. And I want to thank all the GHI executives and reps that are on board and everybody that has connected this evening. Thank you so much for making time, and let's make good use of this knowledge and make Ghana a better place. Thank you all.
Thank you very much indeed, Yvonne. I wish I had the time to do a vote of thanks to you, Yvonne, for putting you on the spot. Very good. Well discharged as an engineer, improvised. So we thank you very much, Yvonne. And Prof, on behalf of GHIE, especially the electrical division, we thank you very, very much indeed for spending time with us. Thank you very much indeed. And thank you all the attendees and for your rapt attention. Thank you very much.
Thanks. And
bye, everyone.
Yeah.
Thanks, Prof.
Thank you.
Bye.
Is there, hello?
Hello. I
was just wondering if there's a way we can connect, let's say via email, LinkedIn.
Yeah. Kingsford, you can make my email address available.
Okay, I will.
Yeah.
Okay. So is that Michael?
No, this is Jonas. This is not Michael. This is Jonas.
If
you can leave that in the chat for me, yes.
Okay. Okay, Henry Jonas. Okay.
Engineer sir, please, I would be interested in connecting too. So if the email can be extended, thank you.
Okay. Okay. So I'll leave that in the chat. Thank you very much indeed.
Okay.
Prof, it's used to giving his numbers to students, so I don't think he's. If you're an academic, people want to follow you a little bit. So, Prof, if you don't mind, I'll put your email address.
Yeah, you can share it.
Thank you very much, Prof.
Okay.
Okay,
right.
all the best. All the best. Bye.
Okay, yeah, speak to you later. Bye.
Yes, all the best. Bye. 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 Okay, gentlemen and ladies, I'm looking for Prof's email address. Let me look for it quickly and put it in our chat. So, Prof, thank you very much indeed. We've taken enough of your time.
That's all right. That's fine.
Thanks.
Okay. Cheers. Bye.
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 Bye-bye.
Bye. Well, Henry, are you still online? Hello, Henry. Oh.
I'm still here and I'm still online.
Yeah, I can't find it now, but I'll share it with you.
Okay, so if you can,
what's your
if
phone
you
number?
can, okay, 020.
Hang on a second.
Sure.
Where's my pen? Oh, 020 Henry 020
158
158
6330.
6330. Okay. I'll
Yes.
send a text
Yes.
message once I find
If you
it.
can check your chat also, I think I've sent my business card, so for easier
Oh, okay.
access. Yeah.
Okay, let's hope I can find it. All right then. Thanks very much.
Thank you
Ineas,
very much.
please, I've sent you my number via the chat too.
Okay. Well, let me